Hi, I'm Chris Kanish, and this is CS361, Systems Programming. Let's get started. Today's video is about processes. We're rounding out the idea of exceptional control flow. One of the most important building blocks of running programs on a computer is this concept of a process. And we're going to start seeing a few of the different ways that the CPU and the operating system lie to your code to make everything work out correctly. So one of the biggest lies that we've been telling to your code is what addresses of the memory it is running at. There is this myth that every single one of these processes has control of the entire address layout, everything from 0 to 2 to the 64 minus 1, and it's the only one that's reading or writing any of those bytes. So that is, without a doubt, not true. We're going to go into a lot of the ways that we actually make that work efficiently in the next module. But for now, what we really need to keep track of is the fact that every individual running process has its own view of the world that simplifies things by allowing it to not have to intentionally cooperate with the other processes that are running on the machine. The reality here is that the kernel, along with the CPU, is multiplexing access to the resources of the computer in a way that allows each of these processes to run fast, efficient, and simply so that they don't have to worry about all the other processes. So when we're talking about a process, we talked a little bit in a previous video about how fundamentally a process just consists of its memory layout and its registers. Here we've got that handy dandy drawing we've seen of the memory layout of a running process, and the list of registers from the x86-64 manual. In addition here, I've kind of got the definition of a task struct. So from the perspective of the kernel, all the different processes are kept track of in their own task struct entry within an array of the different processes that are running on a given operating system. So each of these processes fundamentally has state, right? It has what's in its memory and it has what's in its registers. It also has a little bit of metadata that the operating system is going to be keeping track of, like which areas of memory does it have access to, and how do we translate between its crazy fake idea of what its virtual address space is, and what are the actual addresses of the memory banks where those bytes are physically stored in chips of silicon. In addition to that, every process can be in one of three different states. It can be running, where it's actively on the CPU executing instructions. It can be ready, where it's in a queue, which can start running instructions as soon as it is given access to the CPU. Or it can be blocked, where it has gone to sleep either intentionally or accidentally, and if it were given access to the CPU, it wouldn't be able to make forward progress in its program. There's no good reason to put that program back on the CPU at that moment in time. One reason for this happening would be a web server that is waiting for somebody to come and make a request. It doesn't have anything to do because no one has made any requests. Or it can be your program. Like if your program needs to open a file from the disk, read in a bunch of bytes, and then do some computation on it, when it first says, hey, operating system, open this file, if that file is on an SSD, or especially if it's on a rotating disk, it can be 10, 15 milliseconds before that file actually can be opened. Millions of instructions can run in those 15 milliseconds. So there's no good reason for your process to just kind of sit there waiting, hoping it's going to finish, hoping it's going to open that file. It'd be much better for the computer overall to put that process to sleep, wait for it to finish loading the bytes from the beginning of that file or from the file system to figure out whether it's allowed to open that file. And then eventually start it back up and allow it to continue running whatever its next instruction is. So our goal with having this process abstraction and having this task struct that keeps track of a list of processes, what we want to do with a modern computer, whether it has one CPU or multiple CPUs, is run multiple processes at a time, multiple instances of programs that are stored on that computer's disk. Fundamentally, we want this execution to look simultaneous regardless of how many CPUs we have access to, because at the end of the day, most modern computing doesn't keep the CPU pegged 100% of the time. It's possibly trying to do a little bit of this, a little bit of that, and it's only going to be happening in response to some stimulus, whether it's somebody clicking a mouse or a packet coming in off of the network. In reality, a lot of programs just don't have anything to do a lot of the time if they're not explicitly set up to be performing computation 24/7. So we got a few interesting questions about how we can actually achieve this with a modern CPU and a modern operating system. One of the most important decisions that we're going to make, both with respect to how an operating system does it, as well as any situation where we're trying to do different tasks at the same time, right? So we're going to be learning about this with respect to operating systems coordinating the multiplexing of processes onto the hardware of the computer. The same set of skills we're going to use to decide what design decisions we make and what implementation details we have are the same ones you would use if you wanted to multiplex the tasks of a web server or the tasks of a database engine. If there's lots of different things that are potentially coming in that all need to happen, that have a collection of instructions, and I need to multiplex them, there's a few different ways that we can do that. One of the biggest decisions that you'll potentially make in this situation is whether you're going to be doing preemptive multiprocessing or cooperative multiprocessing. Preemptive multiprocessing is what we use in basically every operating system that you will come in contact with on a normal day-to-day basis, even as a developer. Preemptive multiprocessing posits that every program thinks that it has full control of the CPU for all time and full control of the memory address layout for all time. That abstraction is incorrect, right? That's not the reality of the situation. But by exposing that reality to the process, it makes that process's job a lot easier. Like if you want to, in a preemptive multitasking world, compute 1 trillion digits of pi, you write your assembly code where you just make a random guess, see if it's in the unit circle. Make a random guess, see if it's in the unit circle. Make a random guess, see if it's in the unit circle. Over and over and over. You don't have to do anything. Your process thinks that it has full control over the entire computer. It doesn't have to coordinate with anybody else if it doesn't want to. The reality is that the operating system is going to conspire with the CPU to yank your code off of the CPU every once in a while and allow other things to happen. You do not have control over when your program stops running or not. Preempting something, literally in English, means getting in front of it and running before it runs. That's what a preemptive multiprocessing world allows us to do. This is good because it makes things more simple. It's bad because we need to find some way to effectively freeze something that isn't even aware this is happening and then resume it without having any sort of incorrect operation. But overall, it's pretty popular, especially for scheduling things at the operating system level. It makes running lots of programs written by lots of different people that don't know each other, don't speak the same languages, weren't compiling the same languages, to more or less cooperate by just not knowing each other exists. The other fundamental approach to running multiple tasks on the same computer is cooperative multitasking. This is where every individual process knows, for some definition of knows, about the other tasks that need to happen. When it knows that other tasks are potentially going to happen, it needs to voluntarily cede control of the processor and allow other processes to run. In certain languages like JavaScript, this is just the way things work. Your code runs for as long as it wants to run and it won't get preempted. It will keep going until it decides to say, hey, I've had enough time. Let's check to see if other things need to be run. This sounds, and it is, a lot more complicated than our preemptive approach, where there's a lot more coupling between task 1 and task 2. Task 1 kind of has to know that task 2 exists. Might not need to know what it is, but it needs to know it should check for it, right? That has to happen in your code in some way, shape, or form. So that's a negative here. It's negative in terms of complexity. We're coupling the idea of multitasking with the user level code of that process, where in preemptive code, our code doesn't have to do anything with preemption. The CPU and the kernel take care of preemption. Our code does its one thing, does it as fast as it can. It ignores the rest of the world. Cooperative code needs to know that it needs to do cooperating. It has to voluntarily do it as part of its instruction set. The advantages that we get out of cooperative code is that we're never going to get interrupted in the middle of something. So if we have some cache locality, if our code is running really fast because everything's in L1 cache, we can just do the processor intensive things that we need to do. And as soon as we're done with that chunk of code, we can say, aha, I'm at a good stopping point. I've gotten a lot of efficiency out of being able to run without getting interrupted. I'm going to let go. I'm going to let someone else start. That ability to control when we switch from one task to another allows you to have high performance processing. JavaScript gets a lot of mileage out of this. Modern web servers get a lot of mileage out of this, but it does come at a cost, and that cost is increased complexity and increased coupling between the different responsibilities of the code and the operating system that are fundamentally supposed to be doing different things, right? Best case scenario, the operating system deals with scheduling tasks, and the user level code takes care of the user level stuff that users care about. Every operating system I've ever used, every operating system you're probably ever going to come into contact with, does preemptive multitasking for its tasks. So now that we have this idea of how we're going to share access to one specific CPU, we're either going to rip it out unbeknownst to the user level code, or we're going to cooperatively switch from one task to another. We need to know how we're going to do that. Conceptually, what we're doing here is pretending there's one CPU, but it's just really ridiculously fast. And I'm going to switch between running process 1, then I'm going to swap out, I'm going to run process 2. I'm going to swap it out, I'm going to run process 1. I'm going to swap it out, I'm going to run process 3, whatever the heck it is. Because the CPU is so incredibly fast, if these processes aren't trying to do really complicated things, or if the operating system isn't configured such that each of those processes run for a super long amount of time, it'll look to a normal human being like those 3 processes are running simultaneously. In actuality, they're not running simultaneously. One of them runs for a certain amount of time, gets swapped out. Another one comes in, runs for a certain amount of time, swapped out, etc. If all 3 of those tasks have an infinite amount of work to do, the operating system is going to give each of them what's called a quantum of time to run instructions. What will fundamentally happen is at some point, the kernel gets control of the processor. The kernel says, okay, I'm going to put myself to sleep and start process 1, but in 10,000 ticks, CPU, I want you to cause an alarm to happen, which will transfer control back to me, the kernel, so that I can say, hey, has this process used up its fair share at this moment in time? If so, transfer control over to a different process and run that one for 10,000 ticks. Then run the next one for 10,000 ticks. Whichever one is ready to go, which could start running instructions as soon as it gets given access to the CPU, it's going to give control to that process, and it's going to try to be fair about sharing the time between the different processes that are potentially able to run at any given moment in time. This gives the appearance of parallel computation, even if you have a system with one CPU. When we generalize from one CPU to multiple CPUs, we're kind of sort of doing the same thing. Remember what I was trying to say before, that the kernel never runs in and of itself. It's always running on behalf of an individual process. If I have 2 CPUs, and even if I'm in kernel mode on both of them, I'm running in behalf of one process on one processor and on behalf of another process on another processor. There was a lot of really hard work that went into translating Linux from a kernel that runs fundamentally on one CPU to a kernel that can run in multiple places on multiple CPUs. But at the end of the day, this concept of time sharing isn't going to change much when we go from one CPU to another, because we're always running individual user level processes. It's just that sometimes we're running those processes in kernel mode on behalf of the operating system, as opposed to on behalf of the user level code itself. So if we take our drawing and bring it a little bit closer to reality, it's going to look something like this. Each of these individual processes is connected to the kernel, and each of them has a user level stack and potentially has a kernel level stack as well. If, for instance, one process was halfway through using the kernel to open a file and it ran out of its time, it ran out of its quantum, the operating system can swap from running in kernel mode on behalf of an individual process to running in kernel mode on behalf of another one, then swap over to the user level code. Remember, there's user level text, there's kernel level text. And when there's text, there's going to be a stack. So you've got every single one of these has its own user level text. Every single one of them has its own user level stack. But on the kernel side, there's only one text, and each individual process can, but doesn't necessarily have to, have a kernel side stack. If the exception handler hasn't been called yet on behalf of that user level process, then there's nothing to be on that stack. The next time we transfer control into the kernel on behalf of that process, it will create a kernel level stack frame. But until then, there just isn't one. Remember, the kernel is a collection of exception handlers that work as procedure calls. And whenever there's procedure calls, there's stack frames. So as we continue to drill down into how we run multiple processes on a operating system at the same time, we're going to get to this next concept called yielding. So this is when we go from running one specific process to running some other process. Sometimes this is going to happen because your process has used up its quantum, as we were talking about earlier. Say it gets 10,000 ticks to do jobs, and then it's somebody else's time for a fair share. The other way that a process will stop running before its 10,000 ticks are up is if it starts trying to do something that will take a long time, but won't take up the CPU itself. So opening a file on a spinning disk is a good example of that. You have another instruction and you are eventually going to run it, but there's nothing for you to do until that file gets open. And if there's nothing for you to do until that file gets open, you're just going to voluntarily give up access to the processor, and the kernel is going to pick another process to start running. This, for lack of a better word, process of going from running process 1 to running process 2 is called a context switch. When we're moving from one to the other, we've got to save our state in process 1 and move over to process 2. Remember that this is similar to a procedure call where we're going to push things onto the stack and then we're going to pop them back out into the registers, right? We're going to do the same thing here, but rather than going from one stack frame to another stack frame, we're going from one stack frame in one process to another stack frame in another process. So there's a lot more we've got to save and restore than just our registers of our local execution context. We've also got to save which process we're running, what our virtual memory map looks like, what instruction pointer we're on, etc. So fundamentally, when we switch from one process to another, very similar to a procedure call. In a procedure call, we push our registers onto the stack to save them there. And when we return from that procedure call, we pop them off of the stack, back from the memory of the stack into the individual registers, including, importantly, that instruction pointer that points to the next instruction to be run. The same thing is going to happen here, where in addition to saving our general purpose registers, as well as our stack pointer and our program counter, we're also going to switch which process is running. So we tell the CPU, rather than running with this map of what memory lives where, run with this map of what memory lives where. That new map that is associated with that individual running process will cause the next instruction that runs on behalf of process 2 to access its physical memory rather than the original process's physical memory. One kind of tricky, but still elucidating example that we can do here is to think about two copies of the same exact program. So here we've got process 2, which is an instance of bash, and we've got process n, which is also an instance of bash. If we're going from n to 2, for instance, there's going to be some address like the global variable status, something like that. There's something called status, and it's at address 600. And the status of this process is 4. Now, because this other bash is the same program running in a different process, it also has a symbol called status. That symbol also lives at address 600, but this one's status is, say, 8. What happens in a context switch is not only are we going to be saving our registers, like in a procedure call, we're also going to be switching the mapping between these virtual addresses, which we're going to learn a lot more about later on, and where it is physically stored in the memory of the running computer. So this map of what does this 600 map to? So this is our virtual address, and this is our physical address. So in this world, we've got this 600, but that 600 is just a virtual address. In actuality, it maps down to some address 1 in memory. Likewise, in this other running process, because they're independent copies of the data section, they each have to have their own copy because they're read-write. This one might map down into address 2. So rather than swap out all the memory from one instance of bash to the other instance of bash, what the kernel and the CPU do is they swap out the mapping between the virtual addresses of the running process and the actual physical silicon RAM chips that are installed in your motherboard. That mapping is another incredibly important part. So this switching text and data, what we're doing is not physically pulling all the text and data out and shoving them into some other place. What we're doing is saying, listen, every single process has an address layout, and those addresses point to real physical places on real physical RAM chips. What the CPU and the kernel do is they swap out that mapping such that when we're in process N, 600 maps to 1. But when we do a context switch, all of a sudden, 600 maps to 2. This mapping is something that has to happen for every single load in every single store. So it is supported by very, very fast memory in the processor and by the way that the processor was designed itself. The important things to remember about context switching is they work like procedure calls, and that they pause one thing and move over to another. You could imagine, just like a procedure call, it will be effectively the same exact process in reverse to go from running process 2 back to running process N, or running process 2 to running process 1. Eventually, you're going to be popping the saved context of that process, which is stored down there in kernel memory, back into the registers. You're going to, you as the kernel are going to say, hey, CPU, wake me up in 10,000 ticks if this process is still running. You're going to set yourself to sleep, and you set yourself to sleep by telling the CPU the next instruction should be this one of process 2, or the next instruction should be this one of process 1. At that point in time, you switch from being in privileged mode back over to unprivileged mode. The kernel is no longer running. It is completely swapped out. It has no control over what's happening. Only the CPU and the user level process have control over what's happening until another exception happens, until we go through this exceptional control flow again. That's all I've got for you right now on these sections of Chapter 8. Thanks so much for watching, and I'll see you next time.